Yes. Hey, welcome back. Now let us solve the problem route to leaf path. And the question is like straightforward. Like you are given a binary tree of nodes, and you have to find all the possible paths from the root node to all the leaf nodes of the binary tree. So what does it mean? Let us look at this example. So you have a binary tree like this. So what are the possible paths? 10, 20, 40, which is the first part. 10, 20, 50, which is the second part. And 10, 30, which is the third part. So you just have to draw the paths. So how can you do this? And if you have watched my previous videos, I have mentioned a way where what we do is from the leaf node, we draw a line to the root. Let us see what will happen if we do that. From 40, we'll draw a line to the root. So 40, 20, 10. From 60, we'll draw a line to the root. So 60, 20, 10. And from 30, we'll draw a line to the root. So 30, 10. And then when we reverse it, we actually get the answer. So yeah, that is one way to solve the problem, which is my favorite, which is nothing but drawing lines. And there's another way to solve this. And that is to have a running path. Like if you have heard about running sum, then running path will be easy to understand. So what we'll do is we'll have a running path which starts from 10. And as soon as we encounter any leaf nodes, we will just add the current running path to our leaves. And then we will just make sure to get the value of leaves. And then we will return the answer. So yeah, first let us do my favorite way, which is nothing but drawing the lines. So let's import the default dictionary and the what do you call DQ from collections. Yeah. And now let us have our q dq, which has nothing but the value of root. And then you will have your mappings again, as usual, which is nothing but a default dictionary which will contain the value of nodes. And you have to do one thing, and that is to map root to -1. So the main reason being that root has no parents. So mappings at the position root is nothing but node with the value of -1. So we have done our precursors. So what we have to do now? So we will declare an array called leaves, which will just hold all the leaf nodes because that is actually essential. And we will populate it now. We'll populate it afterwards. And let's do that. We'll write it when you're going to populate it. Mainly because you can't populate the leaf nodes in any random order. You have to populate it from left to right, like 40, 60, 30. In that order only you have to populate it. And to do that, you have to follow in order traversal. You can't follow any other kind of traversal. Like it won't work out. So yeah, so we will use two kind of traversals over here, which is nothing but in-order traversal and level order traversal. And if you have seen my previous video, then you will know that level order traversal is my favorite. That's why I'm calling that here. If you find any other forms of traversal which does the same work as drawing lines, then you are free to follow it. So what we'll do while q exists or in range the length of q, just pop out the node. Yeah, and if node and node dot left exists, then dot append the value of node not capital A, node dot left. And before that, what you have to do? You have to make the mappings. In other words, you have to draw the line from 10 to 20. First, let's draw the line. So, but make sure to note this. We are not drawing the line from 10 to 20. We are drawing the line from 20 to 10, mainly because 10 has two nodes as children, but 20 will always have one node as parent. And if you draw from top to bottom, what will happen is as soon as you draw from 10 to 20, and when you try to draw from 20 to 10 to 30, what will happen is 10 to 20 node will be replaced. That line will be replaced. So you don't want to do that. So we have to draw from child to parent. So what you will do? Mappings from the node dot left. So you will map it to your actual node. And let's do the same thing for. Sorry, I'm not feeling well. Yeah, let's do the same thing for node dot right also. Yeah. Yes. So now what has happened is you have actually drawn your lines. And this is actually proven that lines are drawn now. You can just do one thing. You can just go through your mappings default dictionary and then check for the lines. Like you can print each value of node dot data. Like you can directly print your mappings mainly because each value is stored as a node. So what you have to do for every value in mappings, You just have to print the mappings key dot data comma value dot data. So now let us do the in order transfer. So we'll have a stack and we'll have leaves over here. Yeah, and so what we'll do while y stack or root exists. So while yeah, there is no need for us to maintain any pointer for root. Sorry, like yeah, there's no need for us to maintain the pointer for root now. So while root exists, so stack dot append the value of root and root is equal to root dot left. And then what you will do? Root is equal to stack. Yeah, root is equal to stack dot pop. And then what you will do? You have to check if the current pop root if root is a leaf node. Yeah, if it is a leaf node, so we'll do for leaves we will append the value of root, and then we will go root is equal to root dot right. So now let's just define our self dot is leaf. Leaf EAF, which will have nothing but the value of self and then the value of node. If by any chance node dot left is none, in other words, if there is no node dot left and there is no node dot right, then what you will do? Return true, telling that it is the leaf node. Or else what you will do? You will return false. Yeah. Now the mappings are also done. So now you have to do the last part of the algorithm. So that is nothing but you will have an answer over here, and then you have to visit all your mappings. So how will you do that? It is 100% guaranteed by now that all your values are stored in order traversal value in order traversal itself. So 40, 60, 30 is how the leaves are stored. So for every leaf in leaves, so what you will do? You will just have a node as you will have a temporary array, and while leaves dot data is not equal to -1, uh, let's travel up like so until our leaf dot data is not equal to -1. So let's go up to 40, 20, 10. But as soon as it reaches the period of time, which is nothing but -1, so it will stop. So while leaf dot data is not equal to this one, what do you call leaf dot data is not equal to -1. So to our temp, we will append the leaf dot data. And then what you will do? You will update the value of leaf. Leaf is nothing but mapping set position leaf. So now what has happened? You have your entire value, but it is in the form of 40, 20, 10. So to answer, you have to append the value of temp, but in reverse order. Yeah. So then you can directly return the answer. And let's just check it out once. And yeah, expected and actual are matching. Yeah, nothing makes me happier than seeing all the problems test cases solved successfully. And yeah, this is one of my favorite ways to do it, which involves drawing lines from the root node, leaf from the leaf nodes to the root nodes, and then reconstructing it. And this is a pretty awesome way. And if you do like this, your interviewer might also be very happy, like seeing some very weird way to do it, where you actually draw lines and all. So now let's do it in what you call a running pathway. So how will you do that? You will do that in the same way, but you'll make some changes over there. So let's do one thing. So we have to travel it in order traversal itself to get the values in the form of like how you want it, and then what you will do. So you don't need a mappings now. So let's remove mappings, but we actually need leaves itself. But what we'll do is that we have to know the current leaf value. What was its running sum? Like I mean running path. So we'll have it as a default dictionary of type and node itself. And what we'll do is that for every value in default dictionary, in our list value, we'll store the value of the current node along with the running sum or the running path. So that takes care of like actually iterating through the like what you tell, like storing the entire running sum for each leaf. So what we will do? So we'll have nothing but root and an empty array just to be sure that what do you call we can, that will be our running sum part, and then you will have It's running path, not the yeah. You have path and running path. I mean, you just have running path, and what you will do? So to your running path, you will assign it as the value of running path is the value of node.data. We have to do like this because people are like arrays are passed by reference. And what will happen is that if you directly modify the running path, like I'm doing running path dot append, you will get the wrong values, and you'll be left wondering where I went wrong. Yeah. And now just let's just remove this path, and let's just remove this path. And over here, what we'll do? Yeah, we'll just add an opening bracket, add a closing bracket, but we'll go two steps back, and we'll add the running path. So now what has happened? You have the running path from every leaf node to the root node. And one more thing to note is that we are actually appending the data itself. We are not appending the actual node. So now again you have stack and you don't want leaves now. You just want an answer variable. And as soon as you see a leaf node, so what you will do to your answer, you will append the value of uh, leaves at the position leaves. And let's just compile it on it. Uh, okay, it's not a leaf at the position leaf, it's leaf at the position root. Yeah, it is very contradictory for leaf at the position root. uh, what is happening? Oh, okay. See, like I made a mistake over here. Like I forgot to add the value of the current leaf also. If by any chance our current node uh, is a leaf, because you have to add the value of the running path to your default dictionary only if the current node is a leaf. So what you will do? Leaves at the position node is nothing but the running path. And yeah, it's working. Let's just submit it. And yeah, as you see, it works. And these were two ways to do it. One was to actually draw lines from our root node, from our leaf node to our root node. And the other one was actually to calculate the running path from our leaf node and from our root node to leaf node. And yeah, that's all for it. And I hope this was educational. And thank you for watching and goodbye.